All right, so we're going to start a new section. It's called conditional probability. And this section is so weird because, first of all, it's like the hardest thing to understand intuitively. It's very, very unintuitive. And I'll tell you what I mean when I say this. But once you organize the information in a particular way, this becomes like the easiest section. So very hard at first, but once you like figure out what to do and how to organize your information, it becomes like super easy. So let me just tell you why I think this section is like the weirdest section and it's so hard to understand. And I'm just gonna give you this. Let's say you go to the doctor, okay? You're visiting the doctor. The doctor says, okay, there's this really rare disease. This disease, it only affects 0.1% of the entire population. It's very, very rare. Barely anyone gets it, right? Okay. Second, he tells you, okay, well, we have this test for the disease, and this test is 95% accurate. Very accurate test, right? And I'll tell you what that means a little bit later, okay? So you take the test and you test positive. Uh-oh, right? Let me tell you this. I want you to figure out what's the chance that you actually have the disease. And I have four options for you. We have 100, 95, 9.5, and 2%. How many of you think it's 100%? Oh, there's one person who thinks it's 100%. All right. How many of you think 95%? All right. 9.5%. All right. 2%? Oh, 2%. All right. I'll give you the answer. The answer to this question is actually 2%.
Wait, I think I know. I think I know why that makes sense though.
Why do you think it makes sense?
Well, it's not, well, the percent of you having the disease may not be as high if you're positive, because if it's
yeah, it's kind of hard to understand why. This is so basically what you're doing is you're trying to find the probability that you have the disease, given that you already know that you tested positive and that the disease like affects 0.1% of the population. So you're like combining two different things together and you're trying to find this probability when you have two statistics going on. Okay. Now, first of all, when you see a test, like for example, like you take a COVID test or something, it says that there's like a 95% accuracy. That means different stuff based on the test. What I mean based on this is usually what happens. And what it means, if you hear 95% accurate, usually what that means is if you test like 100 people, then like 5 people will like be told that they have the disease, okay? Okay, so what this means is you test 100 people, 5 people will be told they have the disease. That doesn't actually mean that they have the disease. They're just gonna be told, okay? All right, so what we're gonna do is we're gonna break this down. I'm gonna give you a situation. And then what we're gonna do is we're gonna figure out, okay, how many people actually have the disease, okay? So let's say I have 100 people, or sorry, 1,000 people. I don't know which one of these have the disease or not. And I literally drew a picture of all these people where every single person is a dot. So there's 1,000 dots right there on the page. I know it doesn't look like it because the dots are so small, but there are actually 1,000 dots.
you do 1,000 dots.
Yeah, I did. I put 1,000 dots on that paper. All right, so here's my first question. Out of 1,000 people, I know the disease has a 0.1% chance of having the disease. So how many people would I expect to actually have the disease out of 1,000? Or at least, how would I figure that out? Remember, the disease has a 0.1% chance of getting it. So what would I do to figure out how many people actually have the disease out of 1,000?
4,000.
Really close, 1,000 times the 0.1%. But remember, 0.1 is a percentage. You can't just multiply percent by like the total. So you would have to divide that percent by 100 to get like the fraction, right? So basically this is 1,000 times 0.001, which is 1. Okay, so based on the statistics that I gave, out of 1,000 people, only one person is going to have that disease. Okay, and let me mark which person that is. Okay, now it doesn't matter, but let's just say it's this first person up here. The first person has the disease. Poor guy. Okay. Yeah, right. All right, second up. How many people would we expect to be healthy? So if there's one person who has the disease, how many people are going to be healthy? 999, right? So everyone else is going to be healthy. Cool. Okay, so next we're going to move away from like the actual disease statistic and let's go into the actual test. Let's say we have 1,000 people. I know that 95% accurate means like, okay, 5 people are going to be told they have the disease out of 100 people. How many, or how would I find out how many people in 1,000 people are going to be told they have the disease? Like
1,000 times 5 divided by 100.
Perfect.
0.05.
Yeah, you got it. 0.05 or 5 over 100. I'll write that the decimal. I like decimals better. Okay, so 95% accurate. That okay, I know that 5 out of 100 or 0.05 people are going to be told they have the disease. So if I want to convert that to 1,000 people, I'm just going to multiply 1,000 times 0.05. That gives me 50. Okay, so let's draw that out here. Okay, so out of my 1,000 people, I know that one person has the disease. Now, what's probably going to happen is the person who has the disease is also going to be told they have the disease. That's probably what's going to happen. So why don't we just highlight the people being told they have the disease by counting 1, 2, 3, 4, 5 down. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So maybe this chunk of people are going to be actually told they have the disease, and a lot of those people aren't actually going to have it, but they're going to be told. Everyone else says, okay, you don't have the disease, you're good. Okay, so in our picture, 1,000 people are told, or 1,000 people are there, 50 people are told they have the disease, and out of that, only one person is actually having the disease. Okay, cool. So let's figure this out. Let's say you're one of the people who actually tested positive for this person. So you're one of the people in that yellow square. Okay. What's the chance that you are the person who actually has the disease? What's the chance that you're the green person? 2%, but how'd you get it?
Oh, no.
You all know. How many total are the people who tested positive? 50. And then how many people actually have the disease? 1 out of 50. And if you divide that together, we get 0.02, which is 2%. There you go. Yeah. So what I want you to get out of this exercise is finding these probabilities where you have 2 different pieces of information. Like, okay, I know that there's a oh my gosh, a 0.1% chance of having the disease, and the test is 95% accurate. Balancing those 2 different things is extremely difficult. To combine them together and actually get a probability out of it, that's really, really, really hard. I'm going to make it easier. Whenever you do a question like this, where you're trying to find something, given that you know something else, it's so much easier to create a table, fill out that table, and then be able to figure out probabilities. It makes it so much easier. So why don't we go ahead and do a different example? I'll show you a way that you can actually do these. And I honestly find these kind of fun. So now before I even go into this, I'm going to introduce some notation. Okay. So up here on the next page, I know it's kind of strange, isn't it? Okay, so let's say we have 2 events. There's E and K. So events are things that can happen, like rolling a 1, being in a classroom, something like that. Okay, and I'm gonna let E be an event that we're interested in. So an event that we're interested in finding the probability of. In our example, E was the probability of actually having the disease, right? So having a disease. Okay. But we're not just interested in the probability of having the disease. We are interested in that probability if we already know that there's another thing that's true that we're going to call K. K in this case was that we tested positive. Okay, what we were doing in the last page is we were trying to find the probability of having the disease, given that I already know that we tested positive. So there's like previous information going in before I find the probability. It makes the total a little bit less, right? We're going to call that the probability of E given K is true. Okay, and we'll show that by using the same notation that we've been using for probability, but we'll put E, what we're interested in, on the left. We'll put this line in the middle, and then we'll put K on the right, or the thing that we already know is true. Okay. No, it's not a division sign. It's like a straight line. Okay. Now, there's a formula for this. I don't really like the formula, so I wrote up my own formula. Okay. It's going to be a fraction. Okay. On the bottom is going to be the number of outcomes where just K is true. Okay, so where only K is true. And on the last page, well, we found on the bottom of that fraction, 50 was the number of people who tested positive. So the only thing that goes on the bottom is, well, just where what we already know is true. That goes on the bottom. The number that goes on top is the number of outcomes where both E and K are true. Okay, and well, if we put that in perspective on the last problem, the number on top was, okay, I know that both having the disease and testing positive was just one person, right? I know that there was one person who tested positive, one went on top. So when I divided 1/50, that's how we got the 2%. Okay, so basically the rule is if I want to find a probability of something given another, we put their intersection up top, like where they're both true, and the number on the bottom is where what we're given is true. Okay, now if that doesn't make any sense, it'll make much more sense when we like are able to organize our information better. So why don't we go through this example here? Let's see, we have a manager of an ice cream shop, and this manager is really curious to tell, okay, what are the different flavors that people like? But there's different things that factor into if someone likes a different flavor or not. For example, if someone's an adult or a child, right? So what this person did is the manager had a bunch of people go in. They asked them, okay, do you like vanilla? Do you like chocolate better? And then they also marked if it was an adult or a child answering the question. So what this manager did is created a table, right? We have a table that tabulates, okay, how many people were an adult and also liked vanilla? And how many people were a child and also liked chocolate? And if the information is organized in this specific way, it makes it really easy to answer these types of questions. Okay, this table isn't actually fully filled out, so I guess we have to go and do that. What goes on in the total columns here, let's do this cell here across from adult. What do you think this total cell represents?
Adults who like chocolate and vanilla, we just add the vanilla and chocolate for adults.
Yeah, right. That basically says the total number of adults, right? So both vanilla and chocolate, everyone goes here is an adult. Okay. So I like what Nico said. To figure out this number, all you need to do is just add across, right? Just add the adults who like vanilla, add the adults who like chocolate. And if we add 52 and 41, perfect, 93. Look at that. Okay, and then the same thing goes for the column or for the cell right below. I can add 26 plus 105 to get 131, and that's the total number of children. Cool. Okay, going down, I guess this cell represents the total number of vanilla, so 52 plus 26 gives us 78, and the total chocolate is 146 by just adding down. Okay. Now, finally, there's a total here. I'm guessing that, well, I guess this cell has to be the grand total, like the total number of people in the entire sample. How do you think I'm going to get that one?
93 plus 131.
Perfect. You can add down. Is there another way we can do it?
Add across to it.
You can add across, right? Either way works. You can either add 93 plus 131, or you can add the 78 and 146. But whichever way you do, you should get 224. Now, what I like to do is I like to just add down, write down the number, and then add across. Because if those two numbers are the same, then you know you've done something right. If you get different numbers, then you've probably done something wrong. Okay, so before we get into these conditional probabilities with the line, why don't we just do a couple normal probabilities? Part A says, I want to know the probability that I choose a child. Okay, well, let's see. If I were to do this experiment and like gather people in my sample and select a child, I would have to gather every single person in my sample, right? So if I don't know anything else about this, I know that the number on the bottom, that has to be the grand total, right? Because I'm selecting a child out of every single person in the sample. So that bottom number has to be the grand total. Okay, and the grand total is 224. Okay, now the number up top, this is just a normal probability. We're just trying to find the number of children, right? So we're just trying to find how many children are there. Well, how many children total are there? 131, right? Now it's kind of tricky because sometimes like what people do is they'll see, okay, I want to know the number of children. They just look to the left of, to the right of children. They're like, oh, it's 26. If you want to find the total number of children, you got to look all the way across the row and figure that total out, right? Okay. So with normal regular probabilities, you're just finding the total of what you're interested in and putting it over the grand total. Cool. Let's do another one. This is still a regular probability that we've been dealing with before. If I wanted to find the probability of, okay, I want to get everyone together, I'm going to select a person out of every single person here, and I want to know the probability that this person is both an adult and that person likes chocolate. Okay, well, it's going to be a fraction. This is a normal probability, like it's just, there's nothing weird about it. We're selecting, we're gathering everyone together and we're selecting someone out of it. So the number on the bottom is still going to be the grand total. Okay, which is still 224. What's the total of people who are adult and like chocolate? 41, right? So we just go up and we find that adult and chocolate. Choco, okay. All right, let's make things a little bit more tricky, okay? Let's say we're doing something more similar to the front page, right? Let's say I already know that I have an adult, okay? So what I've done is I've not gathered everyone in the whole sample, but I've only taken all the adults. So I have this group of all the adults in the sample, okay? I know the person I'm gonna select is going to be an adult because I have all the adults right here. But I wanna know the probability that I select someone who likes vanilla, just out of the adults, not including the children. This is a conditional probability, right? I know that I'm gonna get an adult. I just wanna know the probability that this person likes vanilla, okay? Well, in this situation, I guess this is a conditional probability because we have that line in the middle. I know that E is always the first one, the event that I'm finding the probability of, and K is the thing that I already know. Okay, well, let's see what we can do here, right? Well, on the bottom says the number of outcomes where just K is true. So what number or what am I looking for on the bottom?
Adults.
Number of adults, right? So the number on the bottom isn't going to be the grand total anymore. It's just going to be the total number of adults. Well, how many adults are there?
93.
93, perfect, right? Now, the number that goes on top, if we take a look at our formula, it says the number of outcomes where both E and K are true. So the number on top is just going to be, well, vanilla and adult. And how many people are adults and like vanilla? 52. Perfect. So that's how we go about conditional probabilities. It's so much easier when we organize our information in a chart. Whenever we try to do it in our heads, like the first page, it just gets really messy. And I feel like it's very hard to understand what exactly we're doing. If we organize our information in this chart, it makes it so easy to just stick a number on the bottom, stick it on the top, and you're pretty much good. Okay. Let's do part D. This one, I want to find the probability that we get a child, but we already know that the group of people that we're selecting from is are people who like chocolate, right? So let's do this. On the top, we have the number of things that we, the number of outcomes where they're both true. So child and chocolate. And how many children like chocolate here? 105. And then the number on the bottom is the thing that we know is true, which is the thing on the right, or just chocolate, right? And how many people like chocolate? 146. Perfect. And that's how we go about doing conditional probabilities. It's basically the same thing every time, but if you organize your information well in the beginning, it makes it so easy to just figure out the number on top, figure out the number on bottom, and that's all you have to do. All right. Any questions on example 1? All right. Then why don't we do example number 2? I'm going to give you some time to work on this. We'll come back in a little bit.
We can do the next one.
Yeah. I honestly find these really fun. Let's come back up front here. So in this one we have, let's see, someone went to a school, they asked students, okay, are you taking math or not taking math? And then are you taking English or are you not taking English? So Michael did a good job of like writing out the totals here. I think everyone was on the right track there, so I think we're good here. Let's go through some of these probabilities. So for part A, we want to know the probability just of selecting someone who is taking English. So like nothing is known here. We're just taking someone out. We want to know if they're taking English or not. Nico, did you write this one up?
Yeah,
All right, you want to take us through this one?
I took the total amount of people that were like in it, and then I went to take English and went across to the total category.
Perfect. So English over total. I don't know why I wrote that in the disappearing font. That's okay. All right. Good job there. Part B was finding, okay, not taking math and not taking English. All right, Nico, take us through this one too.
So I again just went through the total entire people that were categorized, and then I went to not taking English, or I went to, sorry, not taking math, and then I went down to not taking English. 42.
Yeah, so that's like where both are true, and then you put it over the grand total. Very nice there. All right, now we have to go to the conditional probabilities. I know it's conditional because the questions like has a line in the middle. So whenever you have that big line in the middle, you know that this is a conditional probability. And Hunter, you wrote these up, right? Do you want to take us through the first one?
I basically wrote the total of everyone taking math on the bottom, and then everyone taking math and English at the top.
Awesome. So this one was both over the just the total of taking math, because this is a conditional probability. Nice job there. In part D, what I did is I just took the same question as part C and I just swapped the two ones. So I swapped taking math and taking English and I put them in different spots. So this time, instead of like, okay, I know that we're taking math, now I know that we're taking English and I want to know the probability of taking math from that set of people who are also taking English. So this one's a little bit different because, well, you might think it's the same as part C, but it's slightly different. And Hunter, do you want to take us through how you got this one?
I wrote the total amount of everyone taking English on the bottom, and then everyone taking math and English at the top.
Perfect. So this one is slightly different. What's going to happen when you flip the two things in the conditional probability? It doesn't matter what order you put in. The number on the top is always going to be the same if you have two of the same things going on in the probability. It's going to be where both are true. But what changes is the bottom number, right? So if you flip them over, the bottom number is always the situation on the right. It's going to be different if the situation on the right is different, right? So the bottom number is always going to change, even if the two situations are the same. Okay, any questions so far? All right, part E was, okay, I want to find the probability that we're not taking math, given that we're also taking English. Michael, you want to take us through this one?
Yeah, so I just looked at the problem between where it's saying that you're not taking math, and then where you're not taking English, that instead of total people taking English is 56.
Awesome. So looks like we have a both over total. Oh, sorry, total English, right? We have that situation going on. All right. Any questions on A through E? So this is honestly, I think it's kind of fun. You're just filling out a chart and you're just figuring out, okay, what goes on top, what goes on the bottom. If it's not a conditional probability, the bottom is always going to be that grand total. If it's a conditional probability, the bottom number is going to be something different, right? So it's going to be whatever's on the right-hand side. All right. Now, I'm taking a look at the next page here. I don't know if we're going to have enough time to go through this whole example. So let me just tell you where we're going. We don't have to have just two situations, right? There are situations where we want to know if someone's like taking the car, taking the train, or walking. So not just two situations going on. So I think what we'll do is, how do you feel about leaving a little early today?